Continue on with rotational motion. We're moving on to kinematics. So let's discuss a little bit about angular versus linear measurements. Linear is sometimes known as tangential. The ratio of any arc length to the radius, so S over R, will be the radian measure of the central angle. So this is how a radian is defined. If R is the radius and S is equivalent to R, then we'll have 1 radian. That's how we've defined a radian. So S is equal to R times theta. We denote distance S with the variable d. So d is equal to R times theta. And the change in distance is equal to R times the change in theta. And theta is the angle measure, but not in degrees. It must be in radians. So d, linear distance, R is the radius, and delta theta is the angular distance. So this is the equation that's used to convert from a linear distance to an angular distance, and vice versa. If you're converting from linear to angular, you would just solve for delta theta by itself. You would divide the linear distance divided by the radius to get the angular distance. So we have our first equation, our first relationship between linear distance and angular distance. We're going to move on to linear velocity, which is the velocity we've always known, and angular velocity. Same thing with linear acceleration and angular acceleration. So this equation that we already know, velocity equals the change in distance over time. Well, we're going to go ahead and substitute our new equation in. So we know that delta d is also equal to r delta theta. We're going to substitute that in for delta d in our equation. We get r delta theta divided by t, time. So if we take a look at just delta theta divided by time, that is the change in angular distance over time, which is angular velocity, omega. So the blue W looking thing you see, that's another Greek letter, omega. So now we have 2 different Greek letters that you've been introduced to. You have theta and you have omega. So delta theta over time, that's angular velocity, and so is omega. So omega equals delta theta over time. Okay, we also know the equation acceleration is the change in velocity over time. Well, let's do the same thing. Instead of just keeping it as v, we want to incorporate omega. So velocity is equal to r omega, the radius times the angular velocity. Linear velocity equals radius times angular velocity. Plug that in and we get r times the change in angular velocity divided by time. This is the change in velocity over time, just like we know it as acceleration. It is now angular acceleration, alpha, a 3rd Greek letter. So we have these 3 relationships between our linear quantities, distance, velocity, acceleration, and our angular quantities, angular distance, angular velocity, and angular acceleration. So we talk about angular when we're talking about things that are rotating. So something that's spinning in a circle is an object that's rotating. You should have noticed a commonality between these 3 things. We notice that our linear quantity is always equal to the radius times the kinematic equations. You already have 4 kinematic equations under your belt. These are the linear kinematic equations, but now we're going to derive the angular kinematic equations with the help of these 3 relationships. So the first kinematic equation, Vf equals Vo plus At, we can substitute velocity. We can substitute r omega in for every v that we see. So these 2 v's right here and right here become r omega, specifically omega final and omega initial. Same thing with acceleration. Instead of writing it as linear acceleration, we want angular quantities. So we're going to, instead of calling it a, we're going to call it r alpha. So substitute r alpha in for a. This is, and you'll notice that r cancels out of each of these terms, which leaves us with omega final equals omega initial plus alpha t. This is angular velocity final equals angular velocity initial plus angular acceleration times time. Very similar to our original equation, but angular quantities. This is the same thing for the remainder of the three kinematic equations. We're left with delta theta equals 1/2 omega final, so final angular velocity plus initial angular velocity times time. Our third equation, delta theta equals omega initial times time plus 1/2 alpha t squared. Our fourth equation, omega final squared equals omega initial squared plus 2 alpha delta theta. Our R's end up canceling out because they're in each of the quantities in all three of the kinematic equations. Well, let's do an example. Let's say we have a bike tire with a tire diameter of 70 centimeters. It's constantly accelerating from rest. So it's starting out at a velocity of 0. It's going to eventually spin at a rate of 120 revolutions every minute. So it's going to spin 120 times in 1 minute. It gets to this speed in 10 seconds. So our givens, let's go ahead and write them down. Our diameter is 0.7 meters. What's going to be helpful for us is the radius. We know that the radius is 1/2 the diameter. So our radius is 0.35 meters. Like we said earlier, our velocity initial in both the linear and angular quantities, both 0. Omega final, the problem tells us that we're going to increase in speed all the way up to 120 revolutions per minute. But we know that when we're talking about angular quantities, we have to be in radians. So specifically with our angular velocity, similar to velocity being in meters per second, we want to make sure we're in radians per second. So our unit for distance now, when we're talking about things that are rotating, is radians. And our time is 10 seconds. Well, part A asks us, what is the final angular velocity of the tire at the top speed? 120 revolutions per minute is the top speed, but it's asking for angular velocity, so the answer must be in radians per second. Well, we know that for every 1 revolution in a circle, the tire moves 2 pi radians. So if we have 120 revolutions per minute, we want to convert revolutions. We want to get rid of that quantity. We want to convert it into radians. So we take revolutions in our numerator, drop it down to the denominator. So for every 1 revolution, there's 2 pi radians. Okay, so revolutions will cancel. And then for time, we have minutes currently, but we don't want to be in minutes, we want to be in seconds. So we know for every minute there's 60 seconds. When you do the math, you'll get 4 pi radians per second, or 12.6 radians per second. Part B, what is the angular acceleration of the tire? So this time we're looking for alpha. Well, given our givens right here, we have omega finals, we have the final angular velocity, we have the initial angular velocity, it's 0. We have the time, and it's 10 seconds. So if we solve for alpha, we get omega final minus omega initial divided by time. Well, we're already in radians per second, so that's good, because we know anytime we're looking for an angular quantity such as alpha, we have to be in radians and seconds. So we end up plugging it in. We get radians divided by seconds divided by another second, so radians per second squared, that's ideal. 1.26 radians per second squared is what the angular acceleration you should calculate. Okay, for part C, what angle does the tire rotate through in 10 seconds? So angle, we're talking about a distance, specifically theta. Okay, our theta that we're looking for is not in degrees, it's in radians. So when we're talking about things that are rotating, once again, it's in radians, not degrees, which means if you're plugging things into your calculator, you should be in radians. So if we're looking for delta theta, we're going to solve. We'll use this second equation, delta theta equals 1/2 times omega final plus omega initial times time. When we do the math, we get 1/2 times 40 pi, which is just 20 pi, or 62.8 radians. And unit analysis, this makes sense. Our unit for angular velocity was radians per second. Times seconds means our seconds is going to cancel, leaving us with radians. Part D, how far does the bike move during that time? So how far would be a linear quantity? We're looking for the linear distance. D. And we know the relationship between D and between linear distance and angular distance. Our linear distance is going to be equivalent to our radius times our angular distance. And our angular distance we found in the last problem was 20 pi. So when we multiply our radius, 0.35 meters, times 20 pi, we get 22 meters. Last part. How many revolutions does the tire make during 10 seconds? Well, we know that it went a total distance of 22 meters. But we need to know how far is it around a whole circle. Well, we know that the circumference of a circle is 2 pi r. So one revolution is going to be 2 pi r. Well, our radius was 0.35. So if we plug in 0.35 meters for our radius, we get 2 pi times 0.35, which is 2.19 meters. That's the distance of one revolution. So if we want to know how many complete revolutions we made, we're going to want to divide 22, it's our total distance, divided by the distance of one revolution. So 22 divided by 2.19, we get 10. So 10 revolutions the tire makes. What is the top linear speed of the bike? So if we are looking for the max velocity, but linear, we're looking for v, not omega. So once again, we know a relationship between our linear quantity right here, velocity, and our angular quantity, angular velocity. So if we go ahead and multiply our radius times our final angular velocity, we get 4.4 meters per second.